Oh, 3.
Yeah, all 3. Can you see? Wait, like, guys, how big do I have to write for you guys to see? Like, is this fine? Can you guys read this? Okay, nice. All right, what time is it? I mean, time for me to lock in, but, you know. All right, it's 5 past, whatever. All right, hi. I'm Wayne. I'm a second-year math student here at Warwick. So I know most of you are probably here for like the whole adding fractions wrongly part, but before that, we're gonna, you know, I'm just gonna give a few as to what the main goal is. So we're gonna talk about Diophantine approximation. So the game is this, right? I have a real number, usually irrational, alpha. I want to see how close I can approximate this guy using just rationals. But there's a catch. I need to make sure that every single fraction I give you has a relatively small denominator, because otherwise it would be like kind of pointless. I could just define a sequence that converges to alpha and, you know, talk ended. So yeah, we want to get, like, you can think of the denominator as like the price you're paying for your approximation. So we want to like min-max it, you know, we want to minimize the cost and like make sure that it can get as close to alpha as possible. So that is going to be the game that we're going to be playing for like the next hour, hopefully. Okay, so maybe we can start with like a very trivial bound, if you will. So I claim that for any alpha, I can get as close, you know, I can get this close to alpha for any alpha, okay? So, not so proof. We put alpha on the number line, right? So let's say I have alpha here. Then I mark every fraction with denominator q. It has to be in between two of them. Right? Because of just, you know, how the real numbers work. So, okay, alpha is in between them, so I get that the gap is lesser than 1 over q, and alpha has to be either closer to this fella or this guy, so the half set. All right? So, okay, we did something. This is like a pretty trivial bound. Can we do better? All right, this is like the main idea that we're going to keep playing. Like, can I get a better approximation than this? So it turns out you can. And when I say like get better approximations, we have like 2 ways to do it. First, I either decrease my constant over here. So okay, I have like really horrible handwriting, so I mean, it sounds like you guys are going to have to deal with it. Decrease to like, let's say a C less than half, or I increase the exponent of q. Right? So right now my q is of exponent 1, and maybe I can, you know, do q squared, q cubed, and whatever. So we're going to start with the exponent because it's going to give us like a better result. And to do that, we're going to add some fractions wrongly, which is probably why most of you lots are here. Okay, just to give a definition, I'm not going to write this down because it's really long. So maybe let's... All right, so f of n, this is the Fourier sequence of order n, and it's basically the ordered list of all irreducible fractions with denominator lesser than or equal to n. So it's quite a mouthful to say. So I'll just give some examples. So f of 3 would be something like 0, 1, 1 over 3. So something like this. So I have all the fractions with irreducible, all the irreducible fractions with denominator less than or equal to 3. Obviously, we don't include 0 because that's kind of stupid. And I arrange them in ascending order. All right. So that's f of 3. Maybe we can do f of 6, f of 4, sorry. So it would look something like this. All right. And maybe like another more, because why not? F of 5. Okay, this is probably going to be wait, where am I? Oh. Okay, I'm missing the 1. And I'll stop because it's a bit embarrassing to get this wrong. Okay, so we have these guys. So maybe let's try to find like some pattern amongst them. So probably there's a few really obvious ones. So any fraction of the previous Fourier sequence will appear in the next one. I mean, no shit, right? Then the missing elements, so if, wait, I should write this down because I need it. Okay, where do I write it? Let's do it here. Okay, so the first one, every element of f of n minus 1 is an element of f of n. Okay, this is a pretty straightforward one. Now, the next thing that you could wonder is, okay, how do I go from f of 3 to f of 4, right? So when I wrote all of these down, I didn't memorize them. There's like a nice way to do it. So every missing element is actually, so let's say to go from f of 3 to f of 4, I have 1 over 4. How do I get 1 over 4? I do 0 plus 1 divided by 1 plus 3, right? So again, you can confirm this. Let's say 2 over 5, same thing. I have 1, wait, yeah, this, sorry. 1 plus 1 and 3 plus 2. So it's like 2 over 5. All right, so that's another thing. So every element in f of n, but not in f of n minus 1, is of the form a plus c over b plus d, where a over b, c over d are consecutive. Okay, so that's what we call the median. The name doesn't really, the name is just convenient for me to say. Okay, that's another thing we could figure out. Perhaps something slightly less obvious is if I take any two consecutive elements and I compute the numerator of the first guy times the denominator of the second guy minus the denominator of the first guy times the numerator of the second guy, I always get minus 1. So let's just, try it. Why not? Let's say I choose these two, right? 1 times 3 is obviously 3. 2 times 2 is 4. So 3 minus 4 is 1. Minus 1, sorry. And you can indulge yourself by checking a few other cases, and it seems to always hold. So, okay. If A over B, C over D are consecutive. Then AD minus BC is minus 1. So I'm going to call this property the determinant because, looks like the determinant. Okay. Is there any more? Okay, there seems to be like 2 more, but perhaps most of you would have figured out already. If I take any 2 consecutive elements, and I only look at the denominator, the sum of them is always greater than n, and the product of them is always greater than or equal to n, because you have this one guy over here, which is a bit annoying. So if they are consecutive, then BD is greater than or equal to n. B plus D is always greater than or equal to n plus 1. Okay, so I'm not going to be proving all of these because I only have like 1 hour. But we're going to take these for granted. And rest assured, these can be proven. If you want the proof, you can always just, hit me up after. Okay, so we're going to use these guys to get a better bound for our question. So alpha minus P over Q. How close is alpha minus P over Q? So we're going to prove a theorem due to Dirichlet. Another Dirichlet theorem. Who's surprised? This is Dirichlet 1812. I've forgotten the statement already, so that's not very nice. So let alpha be a real number and n a positive integer. So Dirichlet's theorem says, if I have alpha a real number and a positive integer, then there exists a rational PQ, P over Q, with the denominator being upper bounded by n, such that the distance between alpha and P over Q is bounded above by 1 over Q times n plus 1. All right? So this is what Dirichlet's theorem says. And an immediate corollary is there exist infinitely many rationals P over Q such that alpha minus P over Q is bounded above by 1 over Q squared if and only if alpha is irrational. All right? These are the only theorems that we're going to prove in this talk. So rest assured it's going to be a very chill talk. You don't really have to process a lot of information. Okay, just to make sure that it's clear, these two bounds are like kind of the same thing, because if Q is like lesser than or equal to n, then Q is definitely lesser than n plus 1, because we're talking about integers. So 1 over n plus 1 is lesser than 1 over Q, and you get this. All right, cool. Nothing too crazy going on. All right, so how would we prove this? So I want to use the Fourier fractions or Fourier sequences somehow. Okay. I want like an inequality of n plus 1. I can get that from here, right? I can get that from this guy. But I need like a b plus d, and they have to be consecutive. So what we're going to do is we're going to find two consecutive fractions such that alpha is in between them. And I'm going to try to use the median, which is this guy, to somehow relate to this bound. All right? Okay, so before we get too excited, let's just simplify our lives. Without loss of generality, we let alpha be in between 0 and 1. All right? This is fairly reasonable because I can always just bump up the numerator of this guy. So, okay, without loss of generality, we assume alpha is this. Now we let A over B lesser than C over D be two consecutive f of n. And I'm considering f of n here because my q has to be upper bounded by n. And we've seen, like, you know, by definition of f of n, it makes sense to just consider f of n. Two consecutive elements of fn, then, okay, with alpha being in between them. Okay, great. So now, we want the median coming into play, right? So just suppose that alpha is lesser than the median for now. The other case would be pretty much the same as you would see how the proof goes. So suppose alpha is lesser than this guy, then I want to bound alpha minus A over B, right? But since alpha is lesser than the median and alpha is greater than A over B, this quantity is lesser than the distance between these two guys. Right? So if you want a picture, something like this. Okay? Cool. So in other words, if I can prove that this quantity satisfies this inequality, then I'm done. I win. Okay? And indeed, it does. There's not much we can do here. We just, you know, do our usual minus operation and see what happens. So this would give us, okay, let's hope I can minus fractions properly. AB plus AD. Okay. Okay, is this right? I think it's right. Seems right. Okay. So the AB's cancel. And since A over B and C over D are consecutive, AD minus BC is precisely minus 1. So this thing is actually just 1 over B, B plus D, right? And then the B plus D comes into play because they're consecutive. So B plus D is always greater than or equal to n plus 1. So this guy, in other words, is always lesser than or equal to 1 over B, n plus 1. And we're done. The other case could be dealt similarly. If alpha is greater, then you just use C over D instead. Then you use the same argument and you get the same thing. All right? Cool. Just to clarify, this is not like the standard way to prove Dirichlet's approximation theorem. The more proper way to do it is using the pigeonhole principle. It's like kind of how the pigeonhole principle became so popular. It's like, yeah, but this is also a perfectly fine proof, I hope. Any objections? No, right? Okay, great. Okay, so now for the corollary, again, we're going to use the Fourier fractions. Pretty good. proof of corollary, we will prove that if alpha is irrational, then there exist infinitely many fractions that satisfy that bound. So in other words, we're proving this direction, because I still have no clue how to differ between if and only if, which is slightly embarrassing. Okay, so what's the plan here? The plan is like, I want to be able to reproduce something like this for all n, right? And I should be able to do that, because why not? But there is a slight problem. When we choose our consecutive fractions, what happens if, because like every element of f of n is in f of n plus 1, right? So what happens is like, if I choose my consecutive fractions, I always get a over b, let's say, being chosen. So it shouldn't happen because life. But we'll just check that it doesn't happen, and we're done. So how do we write this? Okay. So we claim, I claim, that the argument above for all n, right? Then it suffices to show that I cannot have a over b being picked too often, right? Because that would mean that they are too close, and if they are too close, then alpha will in fact be a over b, which is completely absurd because alpha is irrational. All right? It suffices to show that a over b, let's say, cannot be too close / too good of an approximation to alpha. All right? So how would we do this? Okay. Suppose that it does. It is, does. Suppose that it is. Cannot be a two. Okay, suppose that it is, whatever. We note that alpha minus a over b is always upper bounded by the distance between the two fractions, right? And the two fractions are consecutive. So, I'm going to use C over D again, but the point is like, if I keep choosing a over b, and I choose like another consecutive fractions and whatnot, it's always upper bounded by this guy. So again, not much we could really do here. We'll just minus the fractions and see what happens. So this is just your usual arithmetic. Right? Again, they are consecutive. So AD minus BC is always minus 1. And BD is upper bounded by n. So, in other words, this quantity is lesser than 1 over n. Right, cool. So, if I have a over b being chosen for all n, then alpha is a over b. You know, your standard analysis stuff. So that's a contradiction. And using that, we've shown that every time I consider higher orders of Fourier sequences, I must have distinct consecutive fractions being chosen. And out of those two consecutive fractions and the median, either one of them will satisfy my inequality. So I have like infinitely many. Yay. How do I tie things up? Okay. Yeah. So alpha is a over b. A contradiction. Very nice. Okay, so that's for this direction. For the other direction, we're going to prove the contrapositive. We're going to show that if alpha is rational, then there can only be finitely many fractions that satisfies this bound. Oh, yeah, this bound. So, okay, I think you guys will remember the Fourier sequences. Okay, if so now we have which direction? Ah, this direction. So we prove the contrapositive because it's much easier. Okay, so let alpha be some rational, let's say P, wait, I use P over Q there. Okay, whatever, A over B. Let alpha be A over B, then A over B minus P over Q by Dirichlet's theorem, which is there. This guy has to be always lesser than 1 over Q squared. Right? This is just from Dirichlet's theorem. Okay, but on the other hand, this guy is just what? Is just AQ minus BP, BQ. And since all AB, PQ are all integers, we know that this numerator is always greater than 1. Because if it was 0, then we would get that AB is equal to PQ, which would be kind of redundant. So this guy is always greater than 1 over BQ. In other words, we need these two inequalities to hold at the same time. But there can only be finitely many fractions P over Q that can do both at the same time. So, okay. Therefore, both inequalities have to hold. Okay, I don't know how to spell simultaneously, so let's just use at the same time. Okay. Best part about speaking more than one language is like I can always play the English is not my main language card. So both inequalities have to hold at the same time, i.e. we need this quantity to be lesser than 1 over Q squared, but bigger than 1 over BQ. And sorry, this can hold if and only if B is greater than Q, which can happen for only finitely many Q, because B is fixed, right? B is my alpha. All right. Great. So we've actually done a bit more. I don't know whether you guys realized. We've actually gave like a very precise criterion for a real number alpha to be irrational via this guy. So usually what we do is like, like a real number is irrational if it's not rational, but like we don't really know. We don't have like a specific criterion for it, right? But here, I'm saying that if alpha is irrational, I should be able to find infinitely many rational approximations that satisfy that bound, all right? So, yeah. This is like, I guess this is a way you could define irrationality as well, if you are interested in doing so. But, yeah, we've done quite a bit, actually, not just some trivial stuff, hopefully, for you. Okay, so back to the question. So we started with 1 over 2q. Now we have 1 over q squared. Can we do better? Can we improve the bound again? So there's two ways, right? Either I decrease my constant or I increase the exponent. So I've increased the exponent now. Okay, cool, whatever. Let's try to find a constant that's lesser than half. That does that. So Hurwitz in 1891 said, yeah, why not? I can do that. Wait, I don't think you, wait, I don't want these guys. Which guys do I not want? Which one's irrelevant?
That one was your first one there.
It's fine. I want these guys. Saj. Okay. So this is $1891. Actually, I don't know why I grabbed the paper. The statement's exactly the same as the Dirichlet's theorem. It's just a constant difference. Be irrational. Then there exist infinitely many P over Q such that alpha minus P over Q is lesser than 1 over square root 5 Q squared. Okay, so this is Hurwitz in 1891. And the proof of this actually uses the Faraday fractions as well, but I'm not going to go through it because the proof is kind of boring. It's just you have a lemma, and that lemma is kind of like something that came from nowhere, but it holds. And you use that lemma to derive a contradiction if you bump down the constant. Trust me, it's boring. But something interesting to say is that this is 1 over square root 5, right? There's no reason why it should be 1 over square root 5. So there is an edge case such that if I bump this constant down, I know some number that is obviously irrational can't give me the same thing, right? So I don't know about you lots, but when I see the 1 over square root 5, the first thing I thought of was the golden ratio. And indeed, the golden ratio is our edge case here. So if I decrease the constant to something like 1 over square root 8, the obviously irrational golden ratio won't give me infinitely many fractions that satisfy this bound. All right? So we can't do better. This is just because the golden ratio is a little naughty boy. Okay. Just in case you are not convinced, like fully convinced, that this is not so stupid to do, you can get an equivalent statement to the Riemann hypothesis via these guys. So, yeah, it's legit. I swear it's legit. It's not something I just made up. Okay, so again, so we know like we can't do much with the constant anymore. This is like the best I can get. So let's go back to the exponent, which I have, conveniently erased. Can we do better? Can we, Dirichlet's theorem says it's q squared. Can I bump it up, like maybe q cubed or something, right? So what do you guys think? Like just some nods. If you think yes, some nods, no. Okay, I see a few head shakes. I think you guys know the answer, that's why you're shaking your head. So yeah, it turns out no, but not quite. For some irrationals, no. And for the other type of irrational, we don't know. So before that, okay, I don't need you guys anymore. Bro. Okay, I've been dropping like a lot of stuff recently. So, Okay. So just a definition. An algebraic number is, how do I define it? Oh, okay. A number is algebraic if it is a root to a polynomial with integer coefficients. So some examples would be like square root 2, 6 root of 7, the golden ratio, 6 root of 7, the golden ratio. And then, I mean, if you want, you can square root of 41. And 1 plus I, because this guy is a root. But we won't care about like the imaginary stuff here. Just, good to know. Okay, so great, we have a definition. Can we do the same thing? Before going into like the whole bound stuff, can we do the same thing with my irrational numbers? So for irrational numbers, I have a precise criterion for my number, alpha, to be irrational, right? I say that alpha is irrational if and only if this holds. Okay, cool. Can I do the same for an algebraic number? So Duville, I don't know how to pronounce his name. In 1844, he said, yes, you can actually get a precise criterion for any number alpha to be algebraic. So he gave like an inequality of some sort, like that resembles something like this. If it's algebraic, I mean, it's algebraic if and only if something holds. I'm not going to write that down because it's really long. But the problem with Duville's result is that it is dependent on what type of alpha you have. So that is like quite a problem, right? Because in the perfect world, we would want something that just, we want to like generalize stuff. But Duville's result is very specific. So there are some very, very naughty alphas. So let's say I know for a fact, like this guy is algebraic, obviously. Just construct a polynomial if you want. But this guy gives a very bad result. It gives a very horrible bound. So the next goal is to, oh wait, before that, even though Duville's result was horrible, not horrible, I mean, you get like a precise criterion, and that's always nice, but it's not very general. So despite that, Duville constructed the first ever explicit example of a transcendental number, which is this fella. And this guy is a pain to write because you'll see why. This is 0.12345 I'm not going to say 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and I give up. So this guy, okay, this guy, first of all, obviously it's not rational because it's not like the decimal expansion is not periodic. But this guy is actually transcendental. And Duville, using his bound and result, actually constructed this example. So we know that there exist transcendental numbers and algebraic numbers, but how do we find them? That's the game that Duville played. So if you're inclined to, you can try to show that this is irrational. Transcendental. Yes. So people have been trying to remove this so-called dependency on alpha for Duville's result. and they've been struggling for quite some time. The final major breakthrough came in 1955. I don't need these guys anymore. Where I think he's German-born British. Is that right? Wait, let me check. Yes. So this is Roth. He's a German-born British mathematician. Not like it matters, but you know. In 1955, he gave this. Let alpha be an algebraic irrational number. Then, for any positive numbers epsilon and c, that's a c. This inequality, which is alpha minus p over q. Is there an equality? There is an equality. Oh, here's q. 2 plus epsilon. This is only satisfied by finitely many rationals PQ. I'm not gonna, yeah. So this is like a really big improvement because previously you will say, yes, I can give you a criterion, but I need to know something about the algebraic number you're choosing. Roth says, I don't care. As long as it's algebraic, this will hold. So if you haven't noticed yet, Liouville's result came in 1844, and this guy proved this in 1955. So in other words, people were like, you know, the higher order beings of human life, the mathematicians, have been struggling like for a year to remove this dependency. And Roth did it. And for his achievement, in 1958, he was awarded the Fields Medal precisely because of this result. So needless to say, we're not going to follow a proof of a Fields Medalist, but I mean, you can try. I mean, I'm not good enough, unfortunately. But yeah, he won the Fields Medal, and I think this is a really nice way to end my talk here. Right. Any questions? Did I do something stupid along the way? No questions. I did that good of a job. Oh, sorry. Yeah. My bad. My bad.
Do we have a good way of constructing approximations?
Yes. This is a very good question. Okay, I'll give you an example, and you'll see why I don't do it. I didn't go through it. Let's say pi, right? Okay, what's the approximation that we're aiming for? 22 over 7, right? So we have pi. I write it like this. I take the floor, and I write the fractional part. Okay. Then what I do now is I write 1 over the fractional part. This guy is now an integer, right? Because 1 divided by a number smaller than 1 gives you an integer. Then I do the same thing. Again, I take the floor of this guy. Add its fractional part. And I keep doing this. These are what, so I truncate it at some point. So at some point, I just stop writing this fractional part. These are what we call like the convergence to pi. And it gives you a rational approximation that actually satisfies Dirichlet's theorem that I erased again. So yes, this is one way to construct them. And you can try. This guy will give you 1. This guy would give you 7. Trust me. Which is what we want. Yeah. But these guys are like really painful to work with. The notation is horrible, as you can already see. This is not something I would want to write a lot. But yes, for any alpha, I can construct better and better approximations using this algorithm. Okay. Thanks for the question. Any more questions? Yes?
Can you show us how that number on the board isn't an algebraic number by the theorem?
In 10 minutes. Sure, why not? 10 minutes, right? I think I can do it, 10 minutes. Okay, the idea is this. I want to construct a lot of rationals that get too close to that number. Because Roth's theorem says, hey, if I'm algebraic, I cannot get too close to it using fractions with only small denominator. So there has to be some gap, is basically what Roth said. And we're going to use Roth's theorem to prove it. Usually people use Liouville's theorem because it's easier, but I didn't write it down, so. Okay. Where's my chalk? There. This is not my chalk. Where did my chalk go? Oh, there it is. Okay, so what's the claim? The claim is that alpha, which is that monster. I'm not going to write the decimal expansion again, because this is just too painful. It's transcendental. All right? So the proof goes something like this. Okay, so if it's suppose not, then this guy's algebraic. And if this guy's algebraic, Roth's theorem says there are only finitely many fractions, blah, 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 that satisfy this guy. So we start that way. Suppose not, mean it's algebraic. Roth's theorem says whatever Roth's theorem says. We take epsilon to be 1 and C to be, does it have to be 1? Okay, whatever. It doesn't really matter, actually. So Roth's theorem says that alpha minus A over B is upper bounded by 1 over B cubed for finitely many A over B. Okay, so now we try to construct like rational approximations to this guy and show that you can get infinitely close. So we define this fella, Rn, which is this guy. Okay. Now we consider alpha minus Rn. Okay. Alpha minus Rn is what? This guy minus this guy, so I start from n plus 1 instead. Infinity minus n factorial. And this guy is upper bounded by this guy. Right? Because I have more terms over here than here. Okay, so we have this guy, we have this fella, and now we use Ross theorem. So Rn is of the form of like some numerator, doesn't matter really, over 10 to the power of, what's this? N factorial, right? Yeah. N factorial. So Rolf's theorem says alpha minus Pn over this guy is lesser than, what's C? What did I choose my C to be? Oh, 1. 3 n factorial, right? Is this correct, right? Surely? Okay. I have faith in myself. This is correct. So in other words, if I can show that that quantity is, if that quantity satisfies this inequality for infinitely often, then I am automatically, I get a contradiction, because Ross theorem says it can only happen for finitely many, consider, like if we suppose alpha to be algebraic. So, and yes. Okay. This guy is a geometric series. So this is 10 over 9 times 10 to the power of minus n plus 1 factorial, right? Surely it's right. Wait, let me think. Is that right? Minus n plus 1. Yeah. Sure. That's correct. So now we just have to show that this guy satisfies this bound infinitely often, which it does, because I say so. But 3n factorial. And I mean, I can just write this nicer. All right. This guy obviously satisfies this inequality for n large enough. Wait, what is it? Sorry?
I think it actually had an n plus 1 command go to the right-hand side for some reason.
Oh, okay. Oh, yeah. Yes, I did. I guess you can choose your C to be 10 over 9, actually. And then like this guy just disappears. And obviously, this guy is lesser than this guy for infinitely many n. So yes, this is how this fella is transcendental. Okay. Ooh, round of applauses. That's a lot. Any more questions? No? All right, great. If you want like any of the proofs that I have not written down, like the properties of the Fourier fractions and like Hurwitz's theorem and stuff, again, you can hit me up. I have something for you to scan, a QR code, obviously, that will lead you to all the proofs and stuff. All right? It's a comically large QR code because I have no clue how to print properly. Okay, that doesn't work. But yeah, here are the proofs if you want them. And any more questions are welcomed. And thank you very much for being here. Watch me add some fractions horribly wrongly. And I hope you guys have a nice conference. Oh, before that, another closing remark. Arshay, I swear to God, I'm going to get the recording and I'm going to force you to watch it. Thank you very much. Okay, all right, bye. Yeah. Okay.
So the way you have to
to show that there's always curves.
Yeah. But this holds for infinitely many n. Because this guy grows faster than this guy.
Yeah.
Like, so I can take like, I just have to take like n greater than
I know.
function or whatever. But this always holds, right?
Yeah.
So if this always holds, it means that this guy is less than this guy infinitely often.
Wait. Yeah. Okay.
Can?
Yeah.
Sure?
I just wanted to say, you did a great job, Wayne. Well done.
Cheers.
Good job, really. Where's your QR code?
Huh?
Where's the QR code?
Where's the QR code?